Now, in the last video, we have discussed the qualitative explanation to explain the capillary rise. Now, in this video, we will derive the expression for capillary rise or fall. Now, we will derive the expression by two methods. The first method is using pressure difference and the second method is using forces. Both the methods are equally efficient. You can use any of the methods if in the exam asked. Okay, both are equally easy. Now let us discuss method 1 first, that is the method which uses the concept of pressure difference. Now here we are again considering the liquid which weights the surface of the capillary tube. Now, so let us consider that we are using water. Now since we are using water, the water will rise up, right? So, and therefore the surface of the water in the capillary tube is concave, as we already know. Now, whenever the liquid surface is curved, there is pressure difference between the two sides of the surface, right? And if the liquid surface is plane, then there is no pressure difference on either sides of the liquid surface, that we have seen in last videos many a times. Now here the here we can see that the uh, the surface or the water meniscus is concave, and therefore there is pressure difference between the two sides of this concave meniscus. Now point A is, here again you can observe 4 points A, B, D and E. Now point A is just above the concave surface and it is inside the capillary. Point B is just below the concave surface and inside the capillary. Point D is at depth H and it is also inside the capillary. Point E is just below the plane surface, but it is outside the capillary. Okay. Now let us consider that the pressures at point A, B, D and E as PA, P suffix A, PB, PD and PE. Now the pressure at point A is obviously atmospheric pressure. Pressure at point E is also atmospheric pressure because this liquid surface is plane. Okay, this liquid surface is plane and therefore the pressure, whatever is the pressure at a point just above the plane surface will be this, that pressure will be equal to the pressure at point E, and therefore pressure at point E is atmospheric pressure. We have discussed this in the last video as well, the same situation. Now, since the point A is uh, at concave side, okay, point A is at concave side and point B is at convex side. Therefore, pressure at point A will be greater than pressure at point B. Now, as I have told you that, hey, you can observe this pressure at point A is greater than point B because we have seen it many a times that pressure on the concave side is always greater than pressure on the convex side. Point A is on the concave side, point B is on the convex side. Therefore, pressure at point A that is on concave side is greater than pressure at point P that is on convex side. Pressure at point A is obviously PA is atmospheric pressure and it is denoted, let us denote the atmospheric pressure by symbol PO. Okay. Therefore, pressure at point A is equal to atmospheric pressure that is PO. Now, point B is just below the concave surface. So, it is on the convex side, right? So, point B is on the convex side and therefore, pressure at point B will be smaller than pressure at point A, right? So, pressure at point B will be smaller than PO, which is pressure at point A, right? By how much factor it will be smaller? 2T by R. Do you remember? The we have derived in last to last video, we have derived the expression for the excess pressure inside the liquid drop, or it is popularly also known as Laplace equation for spherical membrane. Here this we are treating this con concave liquid surface as spherical membrane, right? And we are using this term is coming from Laplace expression for spherical membrane, right? So the pressure at point B becomes P naught minus 2T upon R. Obviously, it is smaller than the pressure at point A. Now, uh, you are having this, you are already having this knowledge that as you go inside the liquid, then uh, the pressure increases in proportion to the depth, right? That is the pressure at point B. And let us consider, let us imagine some point C below B. Then pressure at point C will be greater than pressure at point D. Why? Because it is as you go inside the pressure in the pressure inside the liquid goes on increasing with increase in the depth in proportion to depth, right? Now here the point D as is situated at depth h from the meniscus and therefore obviously the pressure at point D will be greater than pressure at point B. Okay. Then by how much quantity it will be greater? It will be greater proportional to the height h. And you know that from your previous knowledge, this expression for the pressure is given by the equation H rho g. Okay. The pressure at a point at depth h is given by the expression H rho g, where h is the depth, rho is the density of the liquid, and g is the gravitational acceleration, right? Therefore, pressure at point D is greater than pressure at point B. By how much factor? By which factor? By H rho g. Pressure at point B is what? P0 minus 2TR plus H rho g on account of increase in the depth. H rho g factor gets added on account of the depth h and therefore pressure at point D will be PO P naught minus 2T upon R plus H rho g. Have you understood up to this? I hope you have understood up to this point. Now, we have already seen that pressure acting at point E is atmospheric pressure P0. Now here you can observe that E and D are at same horizontal level. Okay. And you can also observe that the liquid is in equilibrium. What do you mean by equilibrium? Whenever you for find the liquid in equilibrium, you will not observe any motion of the liquid, right? Here, once there is a rise of the liquid, in this case water in the capillary, you will observe that the levels are stable. There is no motion of the liquid. Such liquid is known as the equilibrium, the liquid in equilibrium. Now here, the points E and D are at same horizontal level and the liquid is in equilibrium. Therefore, it's very necessary that the pressure at point E and pressure at point D must be same. And therefore, we will equate what is pressure at point E? P0. What is pressure at point D? We have derived P0 minus 2T upon R plus H rho G, where rho is the density of the liquid, G is gravitational acceleration, and pay attention. What is R over here? R over here is radius of curvature of meniscus. You have learned this concept, radius of curvature. Okay. Capital R is radius of curvature of this meniscus. Now here P naught and P naught, they are common on both the sides and therefore they get cancelled, and therefore you are having H rho G is equal to 2T upon R. But this is not the final expression, because if you consider this as final expression, you will have to find out H can be obtained, H can be measured easily. What is H? H is the rise of the water in the capillary, which can be measured easily. Rho, the density of the liquid is known, G is known, T, that is surface tension, is known, but what about R? R is what? R is radius of curvature of meniscus, and we will not able to measure the radius of curvature of meniscus very easily directly in the laboratory. So what to do? We have to find out the value of this R, that is radius of curvature of the meniscus, in terms of the quantities which can be easily measurable in the laboratory. Which are those quantities? Those quantities are small r. Small r is nothing but radius of the capillary tube. It can be easily measured with instruments in the laboratory. And in terms of theta, what is theta? Angle of contact for given liquid and solid interface, right? Now, these are the standard values, standard measured values which you will get directly, right? So, if you know R, if you know theta, you can find out capital R. For that, refer to the diagram 2. This is meniscus. If you complete the circle like this, then this is center of the circle, and therefore this capital R is what? Capital R is the radius of curvature of the meniscus. Are you getting it? It is radius of curvature of the meniscus. This theta is angle of contact. You have already defined angle of contact. What is angle of contact? It is the angle between the tangents drawn to the surface and drawn to the liquid interface at the point of contact measured inside the liquid, and therefore this is angle of contact theta. It is acute because in this case, because here we are considering water, right? Now here, if I produce this line further, if I produce this tangent further in forward direction, then this angle is also theta. Why? Because vertically opposite angles. Now this angle is 90 degrees. Therefore, this angle is 90 minus theta. Now if you complete this triangle, this is R, by geometry, that is radius of curvature of the meniscus. And if I join this line, what is this? This is small r, that is radius of the capillary tube, right? Now if as I have explained you, if by geometry this angle is 90 minus theta and this angle is 90 degrees right angle, then obviously this angle by geometry becomes theta, right? Therefore now what will be cos theta? Adjacent side upon hypotenuse, that is cos theta will be equal to r upon small r upon capital R, right? And therefore capital R can be written as r upon cos theta. Now let us substitute the value of capital R in this expression. H rho g is equal to 2t upon r. Substituting, we get H rho g is equal to 2t upon r upon cos theta. Therefore, it becomes 2t cos theta upon r. And therefore, the expression for the rise becomes 2t cos theta upon r rho g. That is, if you know the surface tension T, if you know angle of contact, if you know radius of the capillary tube, if you know rho, that is density of the liquid, and the gravitational acceleration, you can find out the rise of the liquid in the capillary easily. So this was the pressure difference method to obtain the expression for the rise, that is H. Now we'll discuss the second method, which is also understand, and in this second method we are going to make use of the forces. Now here let us consider that we are using the capillary having radius small r. It is clamped using say retort stand. It is clamped, the retort stand is not shown. It is clamped vertically and it is partially immersed in the liquid which is contained in this vessel. Now let us assume that the liquid weights the glass. Now if the liquid is weighting the glass tube of the capillary, it implies that the angle of contact is acute. Now here the line of contact between the liquid inside the capillary and the glass wall of the capillary will be this circle, simply this circle, that is circumference of the circle, 2 pi r. I will repeat again. The length of the line of contact, right, will be, imagine, I have drawn this diagram in 2 dimension. Imagine the diagram in 3 dimension, right? The the length of line of contact. The liquid will be in contact with the glass surface, and what will be the length of line of contact? The circumference. If you imagine in 3 dimension, the circumference of the circle having radius r, that is 2 pi r. Therefore, the length of the line of contact between the liquid surface in the capillary tube and the glass wall will be 2 pi r. Now the force of surface tension is tangential to the meniscus, as you have learned the definition of surface tension. How it is? The force of surface tension will act per unit length of line of contact by definition, right? By definition of the surface tension. Now this force is tangential to the meniscus and it is directed inside the liquid. Okay. Now since it is directed inside the liquid, what will happen? It will try to pull the whole capillary tube downwards. But will that capillary tube move in downward, will able to move in downward direction? It will not able to move. Why? Because we have clamped it. We have fixed it, right? And therefore, what will happen? The in response to this action, the capillary tube, the glass tube will exert equal and opposite force of reaction per unit length. Um, per unit length of line of contact on the liquid, right? You can observe this force R is equal to T. The magnitude will be equal to the magnitude of the surface tension, but the direction will be opposite. Now let us resolve this force of reaction which acts on the line of which acts per unit length of line of contact in two components. Again, look at the diagram. T sine theta per unit length is how it is. It is directed radially outwards along the horizontal. Now the second component is T cos theta. How it is? It is T cos theta per unit length is directed radially upwards. Now you can observe that if you consider the if you resolve if the force of reaction is acting at each point on the uh, length of line of contact. Therefore, if you resolve the forces at each point, then you will observe that the diametrically opposite pairs of horizontal components cancel each other because they are equal and opposite. And the vertical components T cos theta per unit length, they will all will get added, and therefore the total force of reaction will act in vertically upward direction, right? And this force will act on the line of contact. Therefore, this force will be given by T cos theta. T cos theta is what? The it is acting per unit length, right? Therefore, we have to multiply it by the total length of line of contact. What is total length of line of contact? 2 pi r. Therefore, the total upward force is given as F is equal to T cos theta into 2 pi r. Under the action of this upward force, what will happen? The liquid in the capillary tube will rise up, and it will rise up till what point? It will rise up till the this upward force will balance its weight, which will act in downward direction, right? If h is the height to which the liquid column rises up in the capillary, then the weight of the liquid which has rised up in the capillary is given by volume of the liquid column into rho into g, that is mass into gravitational acceleration. Volume will be pi r square area into h. So pi r square h will give you volume into rho g. Therefore, we'll equate the upward force, which is upward force, T cos theta into 2 pi r, and the downward force, that is weight of the liquid column of height h, as pi r square h rho g. Equating this and cancellation of few terms like r, pi, etc., we finally obtain the expression for the rise of the liquid as H is equal to 2T cos theta upon R rho g, right? So we have found out the expression for the rise of the liquid in the capillary by the method which make uses of the forces. The first method use the concept of the pressure difference, and here we are making the use of the forces acting on the uh, capillary, right? Now if you this expression, you will observe that this rise in the capillary is inversely proportional to the radius of uh, the capillary tube. If radius of the capillary tube is small, that is if tube is narrow, the height will be, that rise will be more, and if the radius of the capillary tube is greater, that is if the tube is broader, then this rise will be smaller. Now also, if the here we have considered the angle of contact to be acute, but if the angle of contact is obtuse, like in case of mercury, where you can, instead of rise, you can observe the fall. In such case, cos theta, for obtuse angles, the cos theta term will be negative. All other terms are positive, only this term will negative, and therefore height will be also negative. What does it mean? Negative height implies that there is a fall of a liquid, as we observe in case of mercury. So here we conclude with the expression for the rise or fall of a liquid inside the capillary, and therefore we have covered all the theory related with the capillary action or capillarity. Thank you. In the Zoom session, we will solve numericals as well as MCQs based on the videos which we have covered, namely the excess pressure on the uh, sides of the liquid surface, also the excess pressure inside the liquid drop, and the bubble, soap bubble, and the capillarity and dependence of surface tension on impurities added in the liquid, as well as temperature, and also the dependence of angle of contact on various factors. Thank you.